Okay, so in this example, we are going to create a design with multiple logic gates within a module. The particular design we're going to look at is called a multiplexer. And essentially what we're doing is it's the same as the previous video where we did one logic gate, except now we're going to instantiate multiple logic gates within the module and then make sure we connect them together and define the internal wires within the module as well. So this is a very important thing to know in Verilog, because any digital design is simply a collection of logic gates organized and connected together in a particular way. And if you have enough of these logic gates, you can perform very complicated, sophisticated functions. So being able to do this is important, but we do have to recognize that the gate level design flow, which we're doing now, or the gate level way of programming, is not the most powerful, because sooner or later the design becomes so complex it's almost impossible for a human to design at the gate level. This is why in Verilog we are going to very quickly move to behavioral logic, and the multiplexer is actually the best gateway to behavioral designs, because a 2-to-1 multiplexer, as we see here, it's very easy to see how it operates at the gate level, but actually when we look at it we can see that this is simply an if statement. So the behavioral way of designing things in Verilog, we can just describe the behavior of the circuit, and an if statement is exactly what's happening with this multiplexer. And if you're not sure, a multiplexer is a simple circuit in which you have multiple inputs. In this case we have two inputs, A and B, and the output of the circuit will take on the value of either A or B depending on the value of select. If select is 1, the output will become A. If select is 0, the output will become B. This one has two inputs, so it's a 2-to-1 multiplexer. And you can kind of see how this is an if statement, because in human language, or programming human language at least, this would be if select is equal to 1, output is A, else output is B. So we're going to get to that a bit later, but first let's make sure we understand how to do this design at the gate level. And all we're going to do is just instantiate these gates and make sure they're connected up properly. And then we're going to verify the design on the nano board. So I'm going to start a new design for this actually. So we're going to go through the project wizard. I'm going to create a new design in a new folder, and I'm going to call this one multiplexer. So that's going to be the folder, and I'm going to call it multiplexer design as a name. And as we know by now, the FPGA is the EP4C E22F17C6. Make sure you get that right. And finish. So again, we're on the programming design flow. So first thing to do is make a block diagram schematic file. Then we can make a Verilog HDL file, and we can start writing the code for our multiplexer. I'm going to have a module here called multiplexer, and of course we have two inputs, A and B. We also have the select input, and then we have a single output which we'll call out1. So inputs A, B and select. Output is out1. Now, as I said before, this will involve instantiating each one of these logic gates in turn and then making sure they're connected together in the right way. But for the first time, we encounter the concept of the internal wire within a module. So these inner connections we actually have to define as wires and actually give them a name within the module, which we'll get to in a second. So the first one we'll address is the upper AND gate. So the keyword is AND. I'm going to call it AND1. So the output of the AND gate, which always comes first, we have to give that a name. Okay, so that this is going to be one of those internal wires, and I'm going to call it AND1 out. So that's going to be one of the internal wires, and then the two inputs is going to be A and select. Now, because we have a new wire here, we have to declare this wire explicitly within the module like this. So that's the first AND gate. The lower AND gate we'll call AND2. Again, it's going to have an internal wire as its output, and I'm going to call that one AND2 out. So don't forget to create those internal wires. And the two inputs, one input is going to be B. The second input is actually coming from this inverter. So let's go ahead to the next line and create a NOT gate. So the NOT gate is going to have an output, which we have to declare as an internal wire. So I'm going to call it NOT1 out. And the input is going to be coming from select. So notice that with these gates, the output is always the first argument, and then the inputs are the following arguments. So now, because we have the output of the NOT gate, that becomes the input to the AND gate. One thing to note here is the order that we declare these gates does not actually matter. And this is one of the differences between Verilog or any hardware description language and something like C or C++ or any software programming language where the order is actually critical. Now, the reason the order doesn't really matter here is because all of our logic exists in parallel. Okay, it exists simultaneously together. So the order doesn't actually matter. So don't worry if you declare, NOT1 out, or the NOT1 gate was before the AND gate. It doesn't matter as long as those signals are there somewhere. Now, NOT1 out, we have to declare that as an internal wire. Finally, we have an OR gate. So let's declare the OR gate as OR1. The two input, well, the output from the OR gate is going to be out1. That's the output of the whole multiplexer, actually. And then the two inputs are the two outputs of the AND gates. So it's AND1 out and AND2 out. That completes the design for the multiplexer. So let's save. Let's call the multiplexer multiplexer. And then save, and then let's create the symbol file for current file so we can put it into the BDF. So in it goes. So now we need 3 input pins, 1, 2, 3, and an output pin for the LED so we know what the value is. So let's give these pins a descriptive name, A, B, and select. Doesn't matter if it's capital. And then connect them. So remember, these are coming from the switches. And then this one is going to the LED. Let's just give that a descriptive name, LED. So let's save. Let's save the block as block. And then let's do, first of all, make sure the top level entity is the block. And then we do analysis and elaboration because we want to assign the pins. So go to pin planner. And then A is going to be M1. B is going to be T8. The LED is going to be A15. And the select pin is going to be M15. So there's actually a 1-pin separation between select and the two inputs A and B. So let's close that. And now we can do compilation. So remember, what we expect now is the output to take on the value of either A or B, depending on the value of the select pin. So that's complete. So let's go to Tools and Programmer and hit Start and program the board. So now let's take a look and see what we have. So these two are A and B, I think. So let's put them in separate positions. Now, if A is 1 and B is 0, then the output should change depending on the value of the select pin, which is this one. There we go. So at the moment, this is selecting A, I think, which is the second switch. So you can see as that changes, the output is going to change as well. Okay, so I think that verifies the design. So see if you can do this yourself and have a play around with the switches. This is a multiplexer, very important design. We've just done it at the gate level. I think the behavioral level is the right way to do this design. And that's what we'll look at in the future. Maybe in a couple of videos time, we will get to the behavioral level. But yeah, have a go at this and I'll see you in the next one.